Okay, so finally in this chapter, we're going to look at the relationship between delta G standard and equilibrium constant for a reaction. So we went over how to calculate delta G for a reaction under non-standard states. Now, if that reaction is at equilibrium, then the delta G will be 0. And so therefore the concentrations in the reaction quotient will be equilibrium concentrations, so Q will be equal to K. So this will be 0, and then Q will be K. So then delta G standard is equal to minus RT natural log of K. So there are two uses for delta G standard that we have been calculating. One is to get it on your way to get delta G, so that way you can see under the specified conditions the reaction is spontaneous or not, and how much energy you can get out of it if it's spontaneous as it happens, or how much energy you must put into it to make it spontaneous if it's non-spontaneous. So that was one of the uses of this. The other uses is that it's related to the equilibrium constant for a reaction. So let's put that equation to work and see what we can do with it. So again, going back to the familiar reaction, decomposition of, let's do one by one. The decomposition of calcium carbonate into calcium oxide and carbon dioxide. So we are given the delta G standard for this. Sometimes they don't even give you the delta G standard. You have to figure out the delta H standard, delta S standard by looking at the values on the tables. From that, figure out the delta G standard. Once you do that, then you plug it in here and you solve, and by then you're going to be tired. You forgot that this is in kilojoules, so make sure you convert it into joules. That's very important, because R is in joules. That's the number one mistake that's usually made. So once you do that and you solve for natural log of K, then that's e to the power of minus 52.4, which comes out to 1.7 times 10 to the power minus 23. And that makes sense because the delta G standard for this reaction is very positive. So the more positive the delta G standard for a reaction is, the smaller the value of K for that reaction. Which means at equilibrium you have very little products and mostly reactants. So those types of reactions in Chem 1A, we assume they don't take place because you produce so little product that it's almost negligible. So if the delta G standard for a reaction is very positive, that means that the equilibrium constant for that reaction is very, very, very small, which means at equilibrium you have very little products, mostly reactants. So in Chem 1A, we thought those reactions don't take place. So that's one example. Let's look at, and of course the reverse is also true. So for a reaction that the delta G standard is very negative, the value of K will become very large, which means at equilibrium you have mostly products, very little reactants. So the concentration of your limiting reactant will be almost 0. So for example, those complex ion formation, the formation constants for those was very large. So for those reactions, if you were to calculate the delta G standard using the K formation, you'll see the delta G standard comes out to be very negative. Which means at equilibrium you have mostly products, very little reactants. So in Chem 1A we assume those reactions go all the way to completion. So in here, the second example, you have a reaction, you have a weak monoprotic acid, its concentration is 2 molar, and its pH is 4, and you want to calculate the delta G standard for that reaction. And so, it's so hot in here, excuse me, I turn off all the ACs. You set up the icebox like before, and you calculate the K. So this is basically relating exam 3 material to exam 1. So in exam 1, you learned to calculate the Ka if the molarity and the pH were given. So from the pH, you can calculate the equilibrium concentration of hydrogen is 10 to the power minus 4. So that's the equilibrium concentration of hydrogen. You have the initial concentration of the acid and the hydrogen and the anion. And so then you set up the icebox and you calculate the Ka, which comes out to be 5 times 10 to the power minus 9. So Ka is very small. What does that tell you about the delta G standard for this? Well, it must be very positive. So we plug it into here and you solve for it, and it comes out to plus 47,356 joules with only 3 sig figs. When you convert into kilojoules, it's 47 kilojoules per mole, so it's positive. So that's what you will get for this. So the delta G standard for all weak acid ionizations will be a very positive number like you see there. Same with KSV. So those insoluble salts, if you were to calculate the delta G standard for those reactions, like here, silver chloride says the solubility of silver chloride in water at 25 degrees Celsius is 1.9 times 10 to the power minus 3 grams per liter. Calculate the delta G standard for this. This delta G standard also must come out to be very positive, like here. Why? Because the KSB values are usually very small, just like Ka values, just like Kb values. So in order to do this, again, this also relates exam 3 material to exam 2. You have to go from solubility to molar solubility to KSV. This is something that you did for exam 2, and then into delta G standard. So I'm going to let you guys work on this. It's very similar to what we did there, so I'm going to let you guys work on this and see what you come up with.